In this video, we'll talk about calculating the linear coefficient r by hand. Recall that a linear correlation is a correlation in which the plotted points can be approximated by a straight line, and the linear coefficient r measures the strength of that linear correlation between paired x and y values in a sample. The value of r is always between -1 and +1. A value close to +1 shows a positive correlation, a value close to -1 shows a negative correlation, and a value close to 0 shows that there is no linear correlation. So given pairs of sample data x and y, so we have two data sets and they are paired together, we want to see if there is a linear correlation. R is equal to the sum of the z-score for x times the z-score for the data value y, add each of those products together and divide by n-1, where n is the sample size. So let's look at an example. So here we have just 5 data values, and we're saying, is the length of a shoe print linearly correlated with height? This data is 5 data values from a larger set of 40 data values. These data values are from the publication Estimation of Stature from Foot and Shoe Length from applications in forensic science. So here is just a plot of those 5 values over here, and we could say to ourselves, okay, does it look like this is a linear correlation? Well, it kind of looks like as x is increasing, y is increasing. Is there a line? Maybe. It's not like very clear, but we're going to test. We're going to find out what is this correlation coefficient r for linear correlation in this case. So in order to find the z-scores for each value, we're going to need to find a few things. One is that we're going to need to find the sample mean for both x and y. So the sample mean for x would be 29.7 plus 29.7 plus ... plus 27.6 divided by the sample size. The sample size in this case is 5, so we're finding the mean for x. And if we find that sample mean, you can find that it's 30.04. We can also find the sample mean for y. The sample mean for y would be 175.3 plus ... plus 172.7, all divided by 5 as well. And if you calculate that out, you'll get a sample mean of 177.3. So those are the sample means for each distribution. We also need to find the sample standard deviation for each distribution. Recall that the standard deviation for a sample is given by the formula square root of sum of the each data value minus the mean for that data value squared divided by n-1, if we're talking about the mean for a sample. And I'm not going to calculate that out, but just will give a solution, and you can verify it if you wish. The standard deviation for the data values in x for the lengths of the shoe prints is 1.66823, and the standard deviation for the lengths of, or for the heights of these individuals in centimeters, that standard deviation is 4.87391. Okay, so now we need to find the z-score for each of these data values, and we're multiplying the product of the paired z-scores together. So for the first data value we have, is 29.7. So x equals 29.7. We can find the z-score for x. So that's 29.7 minus the mean for the x values is 30.04 divided by the standard deviation for the x values. That's 1.66823. And if you calculate that out, you'll get a z-score of -0.20381. So that's the first z-score for x. And the value that was paired with that, the y value, the height that goes with that value for x, was 175.3. so 175.3 centimeters. Z sub y is then 175.3 minus the mean for y, 177.3, divided by the standard deviation for y, 4.87391. And when you calculate that out, you'll get negative 0.41035. So for our first pair of data values, z sub x times z sub y is negative 0.20381 times negative 0.41035. And that gives us a value of 0.08363. So that's our first pair of points. Now for our second one, we see that zx is going to be the same thing. Z sub x, the z-score for 29.7 is going to be the same because x is the same. So that's negative 0.20381. And z sub y is 177.8 minus the mean for the set of heights in centimeters. That was 177.3 divided by the standard deviation for that set of data, 4.87391. And when we calculate that value, zy is 0.10259. So for this ordered pair of data values, zx times zy is equal to negative 0.20381 times 0.10259. And when we calculate that out, we'll get negative 0.02091 as our value there. Note that this is now a negative value. So this is a negative value because the shoe size, or the length of the footprint, was below the mean for the distribution, but the height of the individual was above the mean for the distribution. So this was a negative z-score times a positive z-score. And so this is sort of arguing against correlation this is arguing for a negative correlation versus this one example would be arguing for a positive correlation. And if we have negatives and positives adding together, that's going to get us a value closer to 0. Whereas if we have a bunch of positives added up together, that'll get us a value closer to 1. A bunch of negatives added up together, suggesting a negative correlation, would get us a value close to negative 1. Okay, so I won't calculate this for each ordered pair, but I think you get the idea. And so then R is equal to the sum of, for each ordered pair, the z-score for x times the z-score for y divided by the sample size minus 1. It's also the number of degrees of freedom. So in this case, that would be our first zx times zy was 0.08363, plus the next one was a negative 0.02091, plus ... The last value, if you calculate it out, will be 1.38043. So we're missing the values for those two pairs in the middle. Divided by 5 minus 1 is 4. And when we calculate that out, we'll get R is equal to 0.591. So this suggests a positive correlation, but have we proved it? At this point, no. So what we still need to do is we still need to check to see if this value is significant, and we do this with hypothesis testing. So this, in this case, would be a two-tailed test. We're just checking to see if there is some linear correlation between the length of a shoe print and the height of an individual. And since we're testing to see if there is some correlation, it's a two-tailed test. Our null hypothesis is that there is no linear correlation, that rho is equal to 0, that the true correlation coefficient rho is equal to 0, versus our alternative hypothesis that there is some linear correlation, that the true linear correlation coefficient rho is not equal to 0. We need some level of significance. Let's use alpha equals 0.05 as our level of significance. And this means that the cutoff is 0.05. So if a value at least this extreme occurs less than 0.05 of the time, basically if the probability that rho equals 0 is less than 0.05, that's the area in these tails, then we reject H naught. Then we reject the null hypothesis and say it is very unlikely that there is no linear correlation in this case, versus if the probability that rho equals 0 is greater than 0.05, we do not reject. And we say, okay, we don't in this case have enough evidence to say that there's a linear correlation between shoe print length and height. So let's look in this particular example. This is based on the sample size and the level of significance. So our level of significance is alpha equals 0.05. This is a two-tailed test, so that means we're using this column, alpha equals 0.05. And our degrees of freedom is the sample size minus 1. So in this case, that's just 4. So this is the degrees of freedom. And our cutoff point then would be 0.811. So 0.811. And we're comparing that with R. R was 0.591. So in this case, R is much less than 0.811. Than the required size of R in order to reject the null hypothesis. And so this means that we do not reject the null hypothesis. And so what we would say is that based on this limited information, so based on this limited sample size, we cannot say that there is a linear correlation between height and shoe print length. In the next video, we're going to look at this using technology with a larger data set and see if we can make some different conclusion.